Okay, so today we are going to now look at, having looked at the wave equation, we're going to look at the diffusion equation in 1 + 1 dimensions. Okay, so the diffusion equation looks like uh, diffusion equation in 1 + 1 dimensions looks like this. Del to u del x squared plus 1 over, sorry, not plus, let's go with minus 1 over a squared del u del t equal to 0. Okay, very good. And so this is a parabolic equation that you can see, and characteristics are just equal to constant. In the xt plane. Okay, so if one poses some, I mean, Cauchy data along a t equal to, constant slice, so thus it's very easy to see that one will not have a well defined problem anymore. Okay, well posed problem. Uh, so no well posed problem. If Cauchy data is specified along t equal to constant slices. Okay, so now suppose one specifies the value of u at a given time t equal to 0. So let's try and understand this a little better. So suppose you specify, suppose u of x0 is equal to some b of x. So this determines, determines del 2u del x squared at t equal to 0, which in turn is going to determine, so this in turn determines del u del t at t equal to 0 from the equation. So this is equal to a squared into d2b dx squared, right? So this is a function of bx. So we do not have the freedom. So this essentially means that no freedom to specify del u del t at t equal to 0. And if you did do it, then this is just going to overdetermine the problem. Okay. Now what we do is, let us consider an example that will show us to what extent a single initial condition can determine this solution fully. Okay, let's do that. So consider an example. Consider an example that shows to what extent a single boundary condition, initial condition, determines the solution completely. Okay, suppose u at t equal to 0 is equal to 1 for x greater than 0 and is equal to 0 for x less than 0. Okay, so you have this. So the first thing that we are going to note is that the differential equation and the boundary conditions are invariant under scale transformation. So differential equation, PDE, and boundary conditions are invariant under scale transformations. And what are these scale transformations? Scale transformation is the following. You have x goes to s of x and t goes to s squared of t for all s. Okay. So this leaves your equation invariant. This also leaves boundary condition invariant. So the solution to this equation has to also obey this transformation. Okay. So this means that the solution must also be invariant. That essentially means u of xt is equal to u of sx s squared t. Okay, so let's do the following. So for t greater than 0, let's take s is equal to, put s is equal to 1 over square root of t. So the equation becomes, equation is a single function of single variable now, which is x over root t. Let's call this y. Okay, so the PDE becomes an ODE. This is very good. So it's d2u dy squared plus y over twice a squared du dy is equal to 0. And boundary conditions are u at minus infinity is equal to 0, u at infinity equals 1. Right? So that is what we have. So the solution one of these solution to this equation, one solution is just u1 equal to constant, and once you do that, the other solution is immediately obtainable, and that one, the other solution, is u of y is equal to a constant times integral y0 to y dy primed exponential of minus y prime squared by 4a squared. And these constants are obtainable from the boundary conditions. So what you have is constant obtained from boundary conditions, and what you have is u of y is equal to twice a by pi root over pi integral minus infinity to y dy primed e to the minus y squared rather y prime squared by 4a squared. In terms of x and y, you can rewrite this as the following: twice a by root pi integral minus infinity to x by root t dy e to the minus y squared by 4a squared. This is t greater than 0. Okay. So now it is important to note that there do not exist any solutions to the differential equation for t less than 0, which would satisfy the boundary condition above at t equal to 0. So what does happen is you can set s equal to minus of so you okay, let's just write this down. T less than 0, no solution. Why is this the case? So set s equal to square root of minus t inverse 1 over square root. Sorry, let's just redo this. 1 over square root of minus t. Then what you get is similar solution, but positive exponent. This does not satisfy the boundary condition. This does not satisfy the boundary condition. Right. So this is what we now see. So this particular way of this particular thing of your having so you're being able to solve that for t greater than 0 and not being able to get get some solution for t less than 0. This has a simple sort of physical meaning behind it. So remember what this diffusion equation does. So diffusion equation is something that describes the disorganization of some physical system, right? So as as you increase time, the thing is going to become more and more and disorganized, and so the entropy is going to increase, and so on and so forth. Now we cannot, if you sort of run time backwards, so it cannot be that a system that has been disorganized for an infinite amount of time suddenly becomes organized at t equal to 0. Okay, so this is sort of intuitively obvious, and this is the feature that the equation itself is trying to say to us. Okay, so that was it for the diffusion equation. And so finally, in the little bit that is left of the lecture now, so we can now go into the Laplace equation. So 2D Laplace equation, this is probably the thing that you guys are most familiar with. But again, we want to look at this from the point of view of what we have been trying to describe. So Cauchy data. So del 2, why do I write u's on top here? Del x squared plus del 2u del y squared is equal to 0. Okay. So what we want to do is we want to find we want to find u of xy that solves this above equation, and with some closed curve C on the xy plane. And now we want this to satisfy, Dirichlet boundary conditions on C. Okay, so unlike what we have been doing, earlier, this is what we want to do. Now this we will see this, and some of this is going to be familiar to you guys. So let's go ahead with this. Okay. Okay. So what do we need to do? We need to find u of xy that solves this equation with some uh, uh, within some closed curve in this xy plane, and which satisfies Dirichlet boundary conditions on C. Okay. Now the point to note is that this is an elliptic equation. So if we are looking for characteristic curves on the xy plane, they do not exist. Okay. So we shall be using very different arguments from the two other things, two other equations that we looked at. Okay. So let me just go through this, and we'll try to. Okay, so let's just write this down. So wish to find u of xy solves, let's call this 1, solves 1 within some closed curve C in the xy plane. And satisfies Dirichlet boundary condition on C. Okay. Now the point to note is that this is an elliptic equation. So hence no characteristic on xy plane. Okay. All right. So let's assume first that our solution, that our problem has two solutions, U1 and U2. There, the difference of this U1 minus U2 will also satisfy Laplace equation in the domain that is delimited by C, and this is going to vanish on C. Okay. If a function satisfies Laplace equation throughout a region enclosed by C, it may be regarded as the real part of some, uh, analytic function. And the real part of an analytic function cannot have a local maxima or a minimum. Therefore, it must take its maximum or minimum boundary values on the boundary of the region itself, where it is analytic. So it follows if the real function of a real part of a function vanishes on the boundary of a region, and where the function is analytic, it must vanish everywhere. So hence, u1 minus u2 is equal to 0, and the solution to our problem is unique. This is an argument which I guess you guys have heard before, but that's the way this is. Okay. So yeah. So you will have a unique solution to our to the thing at hand. Okay. So uniqueness is a tick. Now the existence is in general a much harder thing to prove. So for the case where this C is a circle of radius r, U can be written as r cos theta r sin theta is equal to 1 over 2 pi integral of 0 to 2 pi U at C r squared minus r squared divided by r squared minus twice r cos theta minus theta primed plus r squared. So this is when C is a circle of radius okay. Now since Dirichlet conditions on C are sufficient to uniquely determine the solution, it's clear that if we go about doing the same thing that we are doing, that is, if we prescribe some Cauchy data on C, the problem in general would be overdetermined. Suppose we are exceptionally lucky, and we somehow were able to prescribe this. So in the sense that U at C and del U del N at C were somehow accidentally equal. Somehow accidentally no, so somehow accidentally consistent. So by this I mean that the del u del n that is determined from u alone on C, and the del u del n that we gave in the and that's supplied with the Cauchy data that were accidentally equal. It's obvious that if you have an infinitesimal change in either of these two things, del u del n at C or u of C, this is going to lead to an overdetermined problem. Okay. So a solution that does not continuously depend on the boundary conditions is called unstable. And in this case, as you can understand, this is an unstable uh, uh, solution that we have. And a problem that leads to an unstable solution is not properly stated. So this problem, when you have a Laplace equation with the Cauchy data, it's not it's not properly stated. Okay. So there's going to be a rule of thumb which I will write down. So this will indicate the general sort of correlation between types of equations and types of boundary conditions that may lead to a stable solution of the PDE. So let's call this rule of thumb. Rule of thumb. So this essentially is general correlation between type of equation and type of boundary condition that may lead to a stable solution. So for the case of elliptic equations, this is going to be Dirichlet or Neumann. Yeah, so for elliptic PDEs, and this is going to be Dirichlet or Neumann or Neumann conditions. On some closed hypersurface. For parabolic PDEs, Dirichlet or Neumann on an open hypersurface. And stable solution exists on only one side. Stable solution exists on only on one side. And finally, as we have seen for hyperbolic PDEs. What we find is that we can have Cauchy conditions on an open hypersurface. So in the last case, again, this is something we saw. If the hypersurface is finite, the Cauchy conditions have to be supplemented by either Dirichlet or Neumann conditions on another hypersurface. Okay, so that's the rule of thumb. And finally, to wrap up this section, is we are going to state a theorem. Let's just do a little bit of stuff before that. So consider an equation del k of u dx1 the k is equal to some stuff that we're going to call k xi u del l plus m plus dot to n del x1 to the l del x2 to the n del xn to the n u of xi. So L here is less than k, and L plus m plus dot plus n is less than or equal to k. And finally, k is not necessarily a linear function of its arguments. Okay. Now, what we are going to do is we are going to consider boundary conditions that fix the value of u del x1 up to del k minus 1 u del x1 for a particular value of the variable at x equal to x1 equal to a1. So, so let's write down this equation. So del u del j u del x1 j at x1 equal to a1. This is equal to sum L of j in of x2, x3, dot xn. Okay, so j is going to be 0, 1, dot up to k minus 1. So what have we done? So we have boundary conditions. So these are boundary conditions. Okay, boundary conditions. So boundary conditions fix the value of u del x1, del 2u del x squared, del 3u del x cubed, and so on and so forth up to del k minus 1 u del x1, del x1 k minus 1. Okay. Finally, a function of several variables, this is something that we have seen earlier, is analytic at a point y So a function of several variables is analytic at y I equal to y naught, I equal to 1 2 dot dot L, if it can be expanded, if it can be expanded in a power series. This is something that we have seen before. So f of y1 to y1, y2 up to yl is equal to summation of rs dot 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 t greater than equal to 0, f of rs dot 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 t y1 minus y10 to the r dot 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 yl minus yl0 to the t, and this is convergent if yi minus yi0 is small enough. Okay, so let's take this equation and let's call this equation A. Okay, maybe let's box this equation. Okay, so this boxed equation then means the following. So this is going to be a theorem. This is a theorem. And this is called Cauchy Kovalevska theorem. So this says the following. So the solution to this boxed equation, which we call 1, say, to 1, satisfying the boundary condition, let's call the boundary condition, let's call this 2, satisfying boundary condition 2 in some neighborhood of a point xi equal to ai, where I equal to 1 to n, exists and is unique and analytic in the neighborhood of that point, provided k is an analytic function of its arguments, at xi equal to ai, u is equal to u of ai, del L plus M plus dot N plus del X L del X2 M dot del X N N. This is also at X equal to Xi equal to AI. So it has to be an analytic function of its arguments. And the functions Lj are also analytic functions of their arguments at X equal to Li. So let's just write the last bit down. And Lj are also analytic functions of their arguments at xi equal to n. Okay, so that is what this theorem says, and this is where we are going to end this part of our discussion. So we have now, understood how to deal with different sorts of equations and different sorts of boundary conditions. And I have also stated this theorem at the end of the day, which gives a statement about the existence and uniqueness and analyticity of the solution of general PDE. So from next time around, we would be actually looking at something that some of you may have already seen. This is going to be the Strum-Liouville theory of of trying to solve differential equations. So we will start off by actually looking at ordinary differential equations at first, before we move on to the rest of the things. We'll require this a little bit for things that we will go ahead and do. But yeah, so that's it for the moment. And so we looked at the one-dimensional diffusion equation, said a little bit about the Laplace equation, and then the rule of thumb, and then this theorem at the end of the day. So that was it for the class. Thank you very much, and see you guys soon.